Okay, let's talk about Le Châtelier's principle. So we looked at a diagram like this, I believe, when we first started talking about equilibrium. And instead of country A, this is going to be, I think that was, well, it doesn't matter. If I can't remember, you guys probably can't remember either, so it's fine. This will be Narnia, and this will be Middle Earth. Just because it's more fun than A and B. So here we have Middle Earth and Narnia, and, you know, the border's been open for a while and things have settled down, right? We have people emigrating, moving back and forth, but we have the same number of people moving to Middle Earth as moving to Narnia, and so the populations are stable. Does that make sense? Okay, then an alien ship from Mars comes and takes a whole bunch of these people away. One that's maybe still a little too close to home is that COVID hit Middle Earth really bad and all these people died. Is that too close? It's probably too close. The Martians came. The Martians came and took these people away. That disturbs the equilibrium, right? So now what's going to happen is we've got the people in Narnia are looking over there and it's like, oh, there's empty houses and land and it's, you know, it's not as crowded. And so some of these people are going to move over there to take the place of the people that left. So this concentration or this population is going to decrease, and that concentration, I'm sorry, this is a, what am I looking at here? Oh, okay. I interpreted the arrow backwards. Hence, yeah, okay. I should maybe just start over, but I'm not going to. Okay. So a whole bunch of people came from Mars and landed here, okay? And so now it's really crowded over here. And so more people are moving to Narnia, and this concentration or population is going to decrease a bit, and this will increase a bit. Does that make sense? Sorry, it didn't start out very good. Maybe because that's why I didn't get enough sleep last night. What Le Châtelier's principle says is that if you have a chemical system at equilibrium that gets disturbed, the system will shift in a direction that minimizes the disturbance. So here we had a whole bunch of people put in on this side. So the equilibrium is going to shift to try to decrease that. We've got a whole bunch of people added. Let's move some of those people over here. Try to reestablish a balance. A system at equilibrium tends to maintain that equilibrium. It bounces back when it gets disturbed. So it's also like a stubborn child, right? The child is like, and I can relate to this because I only like new things when they're my idea, right? That's not a control issue at all, is it? If it's my idea to rearrange the living room, that's great. Somebody else rearranges the living room, not okay, right? I'm going to go put it back because that's how it was supposed to be. So the child, you try to change anything and they're just like resisting you, pushing back. That's what the equilibrium is like. You do something to one side and it's like, well, I'm going to do whatever I can to undo that, right? And so it's like, oh, well, you put a bunch of stuff in here. I'm going to move them over here, and I'll show you. Okay. Does that mean that the numbers end up the same as they were before? No. But the equilibrium is reestablished, and if we calculate the equilibrium constant, it's the same as it was before. Okay. So, looking at a chemical reaction, so here N2O2 in equilibrium with NO2. If we add NO2, this is like adding those people to Middle Earth. The equilibrium is going to shift to the left. It's like you added a bunch of stuff over here. I don't like that. I'm going to get rid of some of it. So this concentration will go up when we add to this side. So before we added anything, it was at equilibrium. Q was equal to K, the equilibrium quotient. Immediately after we're adding some product, so Q is equal to, it's the same expression as K. So we had equilibrium, and now we've added a bunch of stuff here. That makes the numerator bigger. That makes Q larger than K. The system will shift until Q becomes equal to K again. There's more than one way to think about this, and I'm kind of touching on several, and I hope that's not confusing. But if you find one that makes sense to you, just go with that. Any questions yet? So here we have the same thing in pictures. We have our equilibrium here, and we're going to add some NO2. This disturbs the equilibrium. So what's going to happen is that some of these added NO2 molecules are going to react together and form more of the N2O4. So we increased the NO2 concentration. Those are going to react to decrease it somewhat in that process, increasing the other side, reestablishing the equilibrium. If we add reactant, the system doesn't like that either. Like, oh, you put stuff over here, I'll show you. I'm going to get rid of it. So it's going to shift away from what we added. Again, Q is equal to K at equilibrium. If we add more more reactants, if we add more reactants, so we're increasing the reactant concentration, that makes Q smaller. When Q is small, the reaction goes forward until Q becomes equal to K. Here's looking at this in graphs. So here in panel A, we have our original equilibriums where we have a concentration of NO2 and a concentration of N2O4. And we're going to add a bunch of NO2. That's the product. That was the first thing we talked about. We're going to add a bunch of that. So that then will begin to decrease in concentration as the reaction goes backwards, and that's going to cause this concentration of reactants to increase. And then at some point, Q becomes equal to K again, and equilibrium is reestablished. These concentrations are different than they were before. But if we take this concentration squared and divide it by that concentration, we're going to have the same value of K. Okay? Here is the other one where we increase the reactant concentration. So we jump that up, and then this is going to come down as some of it reacts to form the product, and eventually equilibrium gets reestablished. The levels here are the same. It cannot return things to what they were, but it's going to do what it can. Okay? This may or may not be helpful to you. You increase the concentration of reactants, reaction shifts to the right towards the products. You increase the concentrations of the products, causes the reaction to shift to the left. You put more in, and the reaction tries to undo that by going in a way that will react those things. And then you can also express it in terms of decreasing. This causes things to shift the opposite direction. I don't recommend relying on memorizing those. I think it's better to think about it being a stubborn child. So let's look at this reaction. It's in equilibrium. What's the effect of adding additional Br2 to the reaction mixture? So we're going to add some Br2. Is it going to shift to the left or to the right? It'll shift to the left, right? It'll shift to the left, yes? As we added some of this, and it didn't like that. So it's going to try to get rid of it. It's going to get rid of it by going that way. Okay? What if we add some BRNO? What's that going to do to the equilibrium? It'll shift it to the right. Does that make sense? We looked at the relationship between pressure and volume of gases, right? The pressure and the volume of a gas are inversely related. We can take the ideal gas law and rearrange it. So this is molarity. If, for these things to stay equal, if I increase the volume, this side gets smaller, then the pressure has to get smaller. If I decrease the volume, the pressure gets larger. One goes up, the other goes down, inverse relationship. And we're going to assume in all of these examples that the temperature is not changing, just to make things simpler. Okay, so here we have a reaction in a cylinder with a movable piston, so it's a container that has a flexible volume. N2 plus 3H2 goes to 2NH3. So if we push down on the piston, maybe we should draw a picture. So there's the lid can move. If we push down on the lid and make it come down here, what does that do to the volume? It decreases. So if we push down the piston, the volume decreases. What happens to the pressure? It increases. If you think about that physical thing pushing down on the piston, you're applying pressure, right? You're putting pressure on the gas, and we can see that physically it's getting lower in volume, smaller in volume, okay? So if we decrease the volume, the pressure increases. How can we lower the pressure? Increase the volume. So if we pull up on the plunger, or the piston, then we can make the volume larger. Everybody okay with that? What happens if we add helium gas? The total pressure is going to increase. Yeah. Are we looking at total pressures here, though, or partial pressures? We're looking at the partial pressure of each gas. If we add a gas like helium that is not one of the reactants or products, the total pressure is going to change, but it's not going to change the partial pressures of those gases. That will have no effect on partial pressures. Of the reactants and products. That one is kind of hard to remember. And it took me a couple years of teaching this course. I only got to teach it once a year, so I had a whole year to forget. And every time I came to this slide, I'm like, oh shoot, what was that again? I remembered it this time. I'm proud of myself. Okay. So let's look what happens here. So if we increase the pressure, right, the reaction is going to shift towards the side with fewer moles of gas particles. The pressure is dependent on the number of gas particles, not on how big they are. And this is a weird thing about gases. It's just the number of particles. So over here, we have 4 moles of gas. Over here, we have 2 moles of gas. So if we increase the pressure, we can change the moles of gas by moving the reaction in the forward direction, because we can combine some of these together. It's not the greatest analogy, but it's a little bit like carpooling, right? So things are getting really, really crowded on the freeway. Well, let's put more people in each car so we don't have as many cars, and then things will be better. Over here, if we decrease the pressure, the reaction is going to try to replace that pressure. It can't change the volume or the temperature. What can it do? It maybe can change the number of moles of gas. So in an effort to raise the pressure against what was done to it, it's going to shift to the side with more moles of gas. So now these guys split up. Now they can take up more space and cause more pressure. This one's a little harder to understand than the volume or the concentration one. Any questions? So decreasing the volume causes this reaction to shift in the direction that has fewer moles of gas particles. Increasing the volume causes it to shift to the side with greater moles. If the number of moles of gas on each side of the reaction is equal, then changing the pressure or the volume is not going to have any effect. And this is what we were talking about with the helium. Adding an inert gas at a fixed volume, we're going to keep the volume the same. We're just putting some more gas in there. It's not one of the reactants or products. That's not going to have any effect on the equilibrium. Okay, here we have a reaction occurring in the gas state. What's the effect of decreasing the volume of the reaction mixture? So let's not try to go to that previous slide and read off of that. Let's think about it. If the volume goes down, what happens to the pressure? The pressure goes up. Okay? The pressure's going up. This equilibrium is going to shift to try to reduce the pressure. So do we want more moles of gas or fewer moles of gas? It wants to decrease the pressure. So then it wants to decrease the moles of gas. I'm going to say that again because it's kind of confusing. So here, we're decreasing the volume. So we decrease the volume, the pressure goes up. This is what is happening to the system. And then we think about the system as like, okay, how does it resist this? Well, the pressure went up. This was imposed on it. So it wants to make the pressure go back down. How can it make the pressure go back down? By maybe combining gas particles so that we don't have as many particles. So we're looking to lower the number of gas particles. So if we look at this side, how many moles of gas are on the reactant side? There's 2 moles of SO2 and 1 mole of O2. 2 plus 1 equals 3. So 3 moles of gas. And over here, how many moles of gas? 2 moles of gas. You guys are very quiet today. I'm going to pretend I heard you say 2. So, a decrease in volume caused an increase in pressure. This was what was imposed on it. How can it change to reduce that? Will it go to the right or to the left? It'll go to the right. It's going to change in a way that will have fewer moles of gas so that it can bring that pressure down. It can't completely eliminate the pressure change, but it can make a dent in it. Any questions? What if we increase the volume of the reaction mixture? So volume increases. What happens to the pressure? It does not increase, it goes down. If we increase the volume, we're pulling the piston up, making the volume bigger, the same amount of gas in there, the pressure's going to go down. So the system then wants to do what? It wants to increase the pressure. It can increase the pressure by shifting in a direction that increases the moles of gas. And is that to the right or to the left? It's to the left. I want you to practice thinking through that. I think it's tempting for students because, right or left, oh, you had a 50% chance. You just guess on the homework. Oh, I got that one right, great. Well, you might not get it right on the exam. Yeah? So try to think about it. What about temperature? Until now we said the temperature was the same. Well, if the temperature changes, the system will shift to minimize that change. So we can think of heat as being a reactant or a product. Remember exothermic and endothermic reactions? Here, just to simplify things a little bit, we're going to assume that the heat is being added or removed at a constant pressure. So when we were changing the volume and pressure, we said, let's assume that the temperature is the same. Here, we're going to mess around with the temperature. We're going to assume that the pressure is going to stay the same. So in an exothermic reaction, exothermic exiting heat is leaving the system, right? So it's giving off heat. Heat is a product. It's producing heat. Hydrocarbons burning are exothermic. So we light the gas burner and it gives off heat, right? Heat is produced by that combustion reaction. Endothermic, endo is like into, heat going into, and so here heat is a reactant. Heat is going into the reaction. So here we have an exothermic reaction. It's producing heat. If we increase the temperature of this reaction, that is equivalent to adding heat, right? Adding heat or adding a product is going to shift away from that. So if we heat up an exothermic reaction, it's going to shift towards the reactants. And this makes things a little more complicated. When we change the temperature, the equilibrium constant also changes. Just be aware of that. If we have an exothermic reaction and we lower the temperature, that's the equivalent of removing product. It will shift to the right to replace that heat. Does that make sense? Endothermic reaction, the effects are opposite because here heat is a reactant. If we increase the temperature, we're adding adding reactant, it'll shift to the right. If we remove heat, we're removing reactant and it'll shift to the left. And so when it shifts to the right, K gets larger. When it shifts to the left, K gets smaller. Remember, K is only changing when we change the temperature. This is a cool demonstration I wish I could do for you, but I can't. So this is a sealed tube that has N2O4 and NO2 gas in it. It's in equilibrium. So here at a very low temperature, I don't know if that's 75 Kelvin or 75 Celsius doesn't make any sense. Or is that a minus? That's minus. Minus 75 Celsius. Cold temperature, that's removing heat from this reaction. The reaction shifts towards the left. The reactant is colorless. We heat this up, bring it up to, is that 26.2? Bring it up to about room temperature, and the tube turns brown. We are adding heat. Adding heat pushes the reaction to the right. And so now we see more of the brown NO2. Isn't that cool? You can make it go back and forth. Unfortunately, it's not just ice that you need, it's dry ice, or actually liquid nitrogen works better. So that's a summary for exothermic and endothermic reactions. So the following reaction is exothermic. They're telling us it's exothermic. They're not showing heat as a reactant or product. We would do well to write it in ourselves. So if it's exothermic, is heat a reactant or a product? It's a product. So plus heat. That's what exothermic means. So what's the effect of increasing the temperature? Shift to the right or to the left? So shift to the left. I'm adding this product, it's going to shift away from that. What if we decrease the temperature? It'll shift the other direction. So if I'm removing this, it's going to shift to replace that. These ideas are actually very useful in industry where you're trying to maximize the production of a reaction. Most reactions are equilibrium reactions and they don't go to completion. Well, you want them to go farther to completion. So here, if we take this and we reduce the heat, if we lower the temperature, more product is going to get formed. And if that's what we want, that's a good thing. Consider the exothermic reaction. 2NO plus Cl2 goes to 2NO with Cl. Which change causes a reaction mixture at equilibrium to shift right? So, exothermic reaction, is heat a reactant or a product? Product. So plus heat. I think if you write that in before you look at any of the choices, it makes things easier. Okay, adding NOCl to the reaction mixture. We're looking at what will make it shift to the right. If I add product, is it going to shift to the right? No, it's going to shift to the left. Increasing the volume at constant temperature. Well, we've got gases here. I have 3 moles of gas on the left and 2 moles of gas on the right. If I increase the volume increases, what does that do to the pressure? Pressure goes down. And the equilibrium wants to do what? It wants to oppose that. It wants the pressure to go up. So what's it going to try to do with the number of moles of gas? It's trying to make that go up. So it's trying to make more moles of gas. Is that going to shift to the right or to the left? It'll shift to the left. There's 3 moles of gas over here. So that's not the answer. increasing the temperature. Increasing the temperature is the equivalent of adding heat. So wherever the heat is, you're adding to the heat if you increase the temperature. Is that going to cause it to shift to the right? No. None of these. So this is the sort of question that could show up on an exam, where we're not just saying, well, we do this, is it shifting to the right or to the left? We're saying, well, what would make it do this? And then we're giving you different choices. Some of them may be pressure, temperature, volume, concentration, and you have to identify and pick the correct answer.